Hello, it's dumplet here. Here's an item on number theory. Find all natural numbers n greater than 2, satisfying the equation, the GCD of 3n plus 2 and n minus 2, plus the LCM of 3n plus 2 and n minus 2 is equal to 40. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now, this is just one of the things I randomly thought of the other day, and I think it's rather interesting because the solution does involve something called, well, one thing that we have to do is to use the Euclidean algorithm. Now, I already made a video on the Euclidean algorithm in the past. Click this card, it's going to direct you to the Euclidean algorithm. It's very helpful if we want to find the GCD of two numbers. Now, in this case, I'm going to use the Euclidean algorithm to write the first term into something more simple. So, by the Euclidean algorithm, I could have GCD of 3n plus 2, and I'm going to specifically subtract 3 times n minus 2, okay? And then the second number will still remain n minus 2. Okay, now, this portion, if you simplify this one, that's going to be 8. So essentially, this would be the same as saying the GCD of 8 and n minus 2. Now, the reason why I want to subtract 3 times n minus 2, well, that's because I want to reach something constant, in this case, an 8. Because with this, we can kind of say that, all right, the GCD of 8 and whatever this number is, certainly it's going to be less than or equal to 8, because obviously the greatest common divisor cannot exceed 8 in this case. So there we go. So we have the upper bound for the first term, the GCD, to be 8. Now, the second thing that should be pretty much obvious is that we know that the GCD of the two numbers, a and b, that should divide the LCM of the two numbers, a and b. Okay? So we could just kind of list down the possible values of the GCD. Now, because the GCD plus the LCM is equal to 40 over here, we can easily check for the possible values of the GCD. Now, since let's just say we're gonna set D to be the GCD of A and B. Okay. Now, so take a look. The first term is divisible by D over here. The second term is divisible by D. So obviously 40 will have to be divisible by D. And we know that D is technically less than or equal to 8. So we could just kind of list down possible values of D such that D divides 40 that are less than 8. So I'll have D to be 1, 2, 4, and 5, and then 8. So we have these 5 values for D. Right? Again, I'm just listing down all the values less than or equal to 8. Now, let me just write down all the possible values for the GCD. We have 1, 2, 4, 5, and 8. Now, obviously, to satisfy the equation, the LCM should be 39 if the GCD is 1. I'm just going to fill up the rest of the things here. So these should be like the pair of values for the GCD and the LCM. Now, let's try to take note that we're taking the GCD and the LCM of the same pair of numbers here, and we can use a nice property that the GCD of two numbers, A and B, times the LCM of two numbers, A and B, that should be equal to their product, right? You can try to prove this on your own, but this is a very well-known property in the GCD and the LCM, and it's particularly useful for this question because, well, we already know what the possible pairs of values are. So what I'm going to do here is, okay, now the GCD times the LCM in the first case, it's going to be obviously 39. And then the second case would be 76, 144, 175, and then 256. Okay, now these 5 values are the possible products of 3n plus 2 and n minus 2 because, well, obviously I'm taking the GCD and the LCM of these two numbers, so the product of these two should be equivalent to, should be equal to these 5. So we're going to take all these 5 cases one by one. All right, now it's not that difficult to get the values, so I'm going to take the values one by one. So we do have 3n plus 2 times n minus 2, okay? Now the first case we're going to have equal to 39. You know, I'm just going to write all the cases down. 76, 144, 175, and 256. Okay, now, we could always just take note of the fact that, well, in the first case, the GCD is 1, all right? The GCD is 1. The second case is 2, 4, 5, and 8. So, what are the factors of 39 that have a GCD of 1? Now, 39 is 13 times 3. So, it can either be 13, 3, or 39 and 1. Now, take a look here. I'm putting the larger number on the left number, 3n plus 2, because it is obvious to us that 3n plus 2 is going to be greater than n minus 2. And this is actually true. If we try to solve for n, it's true for all n greater than negative 2. Now, obviously, it satisfies that because, as mentioned in the beginning, n is greater than 2. So, this will be the possible cases. But if you try to solve for n here, you're not going to get a value because, for example, if I'm going to just follow the left one here, this is going to give me n equals 5, and then n equals 3. But n equals 5 doesn't give 13, and n equals 3 doesn't even give 39. So the GCD of one case, it's actually impossible, all right? So that's going to be the strategy here. We're just going to try to exhaust all the cases and to see which of these are possible. Next, the GCD in the second case is 2. So expect the two numbers to have 2 times something. And then, right, you can kind of see that 76 is 4 times 19. So 76 is 4 times 19. So 19 should be the product of the remaining two numbers here. Now, obviously the left number is bigger than the right number, so it must be the case that it's 19 and 1. No other possible case. Now, if I were to try to solve for n here, I'll get n to be 4. Now, n equals 4 doesn't give 3n plus 2 to be 2 times 19 or 38. So then again, the 76 case, the GCD of 2 case, it's once again impossible. Okay, so trying the GCD equals 4 case, so the factors should be 4 times something and 4 times something. 144, that's going to be 16 times 9. Now, we just have to factor 9. Now, the only possible way to factor 9 is to put 9 and 1 like this, since the GCD could only be 4. It can't be 3, 3. So, we just kind of solve for n again. I'm going to consider just this one. Now, if I solve for n, I'll get n equals 6. But n equals 6 doesn't give 36 for the value of 3n plus 2. So, again, it's impossible. And that's what we're going to do to just the remaining cases as well. So, the GCD equals 4 case is done. Let's try the GCD being equal to 5. The two factors should be 5 times something and 5 times something. Now, 175 is 25 times, it's going to be 25 times 7. So, well, 7 is prime, so the only way to distribute this is 7 and 1, like this. Now, solving for n in this part, it's going to give n equals 7. Try to put n equals 7 here. It's not going to give 5 times 7 though, so the 175 case is once again impossible. Okay, that leaves us with the final case, the GCD being equal to 8. Let's just check. So the GCD being equal to 8, so 8 times something and 8 times something here. And 256, that's going to be 64 times 4. So how do I distribute the 4? There's only one possible way, just 4 and 1 like this. If I try to solve for n in this portion, I'll get n to be 10. And that's good, because if you try to put n to be 10 here, you're really going to get 32. So if n equals 10, 3n plus 2 is indeed 32. So in fact, n equals 10 is going to be a possible case under the GCD equals 8 case, and in fact, it's the only possible answer in the GCD equals 8 case. Now, since we exhausted all possible cases, we found only one value of n. That's going to be the only possible value of n in the equation. Now, obviously, you could go back to kind of check. So, if n equals 10, we can just get that it's going to be the GCD of 32 and 8 plus the LCM of 32 and 8. Let's just check if that is equal to 40. And you guys can try to check. The GCD will be 8. The LCM would be 32. So 8 plus 32 is indeed equal to 40. So there we go. The only possible value is n equal to 10. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye-bye.